Hey guys, this is Angelo, and today I'm going to be showing you how to do arithmetic and geometric sequences with linear and exponential functions. All right, so let's start off with something easy. So this is a linear function, and I'll tell you how you know that. You know that because the jump between each of the numbers is the same. So between each of the numbers, you're simply adding 2 here, right? Plus 2, plus 2, plus 2, plus 2. So this formula is basically going to give you, you can think of this almost as a function, right? So an is going to be the value that gets outputted at whatever n you're plugging in. A0 here, a naught, that's going to be your initial value, plus b is going to be what you're adding every single time. In this case, that's plus 2, and then n is going to be the number in your sequence, right? So for example, we'll get for this one 1 3 5 7 9. We'll get a9 is going to be equal to our a naught, which as we can see here is 1, right? So 1 plus our b, which is what we're adding each time, plus 2 plus 2 plus 2, right? So plus 2, and then n, right? So there you go. So the reason why this works is because, for example, if you were to plug in 0, right? Because this is our 0 right here. If you were to plug in 0, you get 1 plus 2 times 0. This would cancel out. Let me show that for you. So a0 is going to be 1 plus 2 times 0, right? This is 0, so this just cancels out, and you get your a naught is going to be equal to 1. Okay, so in this example, you're going to understand why earlier I said you could almost treat the explicit form as a function. So here, for example, we're going to look at our y-axis, right? So we're going to notice that if we were to make this kind of like a sequence, we get 8, 6, 4, 2, right? Now, what's going on here between each term? You're subtracting 2 between each term, right? So now let's go back to the formula that I told you. It's going to be an is equal to a naught plus b times n, right? So an stays the same here. A naught, now we don't know our a naught in this case, because if we look at this, if you notice, this is technically starting from a1, right? Now, what you do in this case is that if you still want to make a sequence, like if you still want to make the explicit definition of this, right? You'd get your n, but then you'd subtract 1 and put that all in parentheses. Now, basically what you're doing here is that now you're setting the a naught to be a1 as your initial term, because that's what you know. We don't know a naught from here. You don't know what it's equal to when you're at 0, right? So what you can do is that you can subtract 1 from the n, and now your initial a will be a1. This also works if, for example, you start with a3, right? If you start with a3, you'd have a3 here plus b times n minus 3. So that's just the general rule for what you would do in that case. But here, we know that our a1 is 8, right? Plus b, our b is negative 2, because we're subtracting 2 each time, times n minus 1, right? So there you go. Now we have our sequence, right? So we can even write this out as a function, which is why I was saying you can treat this as a function of n, right? Because we have 8 minus 2 times n minus 1. And if you notice, these two are the exact same. They are the exact same thing, because once you plug in an n, you're going to get out a value here, and then you plot that value. So you see, n, when n is equal to 1, right? 1 minus 1 is equal to 0. So this whole -2 cancels out, and you get f of 1 is going to be equal to 8, which is what you get here. Now, also, this is cool also because what you can also do is that you can plug in 0 here. And remember how I said before that we have to write this in terms of a1 because we don't know what a0 is. But now that we have it almost in terms of a function, we can solve for f of 0 here. So f of 0 is going to be equal to 8 minus 2 times 0 minus 1, right? So this is going to be -2 times 0 minus 1 is just -1, right? So -2 times -1 is going to be +2. So you get 8 plus 2, which is equal to 10, which makes complete sense if you think about it, because if we were to come up here, if I were to extend this a little bit, well, that's really messy. If I were to extend this a little bit, right, and come up to 10, we would have a dot here, and it makes complete sense. Because look, you subtract 2 each time. -2, you get 8. -2, you get 6. So that is basically the extent of what you're going to have to do with any kind of linear function or arithmetic sequence in this lesson. All right, so let's try this one problem here, right? So on a warm summer day in Colorado, a parcel of air rises over the Rocky Mountains. It cools at a rate of 5.5 Fahrenheit per 1,000 feet. Now, I'm already going to stop right here. Whenever I see Fahrenheit per feet or literally any unit per any other unit, this sounds like slope to me. Because obviously if you have some graph, right? And you have, for example, in this case, right, you have feet per, and then you have Fahrenheit on your y-axis, right? The rate of change here, aka your slope, is going to be Fahrenheit per feet, right? So basically, this is already starting to sound like slope to me. And now that's important because if we were to look at these two, y equals mx plus b, right? That's the slope of a line, right? And then the definition that I gave you earlier for an explicit sequence, right? A of n is going to be equal to bn plus a naught or a initial, a zero, whatever you want to call it, right? These two are basically the same thing. They are the same thing, which is why I said you can compare the sequence to a function. Basically, you can make it into a function because this is the same thing. Y and a of n are your outputs or what you're graphing on the y-axis, right? M and b are your slopes, and x and n are your inputs, and then b and a naught, a initial, a zero is going to be your initial value, right? So this is a very important concept that you need to understand, that these two are literally the same. And when you're writing a sequence, you're literally just making a function. That is all you're doing, right? So let's go back to the problem, right? So until it reaches its dew point, if the ground temperature is 76 degrees Fahrenheit, this again is important because what it's asking us air, right? This is my air right here, as it rises, right? Which means that the ground temperature is going to be its initial value, right? So write an explicit formula to describe the situation when the air has risen n,000 feet. So let's just do that part first, right? So we'll do part A, right? So like I said before, this is the slope in this case, right? And since the function is in terms of n,000 feet, 1,000 feet is basically just 1 in this case, right? So our slope is basically going to be 5.5, except it's not positive, it's negative because it says it cools at a rate of 5.5 Fahrenheit, right? So basically, that's just a sneaky way of saying that the function's actually decreasing. So if you were to graph this, I'll do it up here, right? If you were to graph this, your function would decrease like that, right? So basically, and also this would be feet, and this would be Fahrenheit. This would be degrees Fahrenheit, right? So basically, let's go back to an is going to be equal to a naught plus bn, right? An is going to be our output or our t of n, which basically this isn't anything special. This is literally just saying temperature as a function of n. This is the same thing as f of x. That's not anything special. Don't get confused by it. This is the same thing as saying f of x, except in this case it's temperature as a function of n, right? So t of n is going to be equal to a0, which is our initial value, which, as I pointed out before, if the ground temperature is 76 degrees Fahrenheit, 76 is going to be our initial temperature, right? Plus b again is going to be our slope. B is going to be negative 5.5 because 5.5 is our slope, but it's cooling down, so it's decreasing. And then n, which is just how high up it is, right? So that stays the same. N is the same. So there you go. There's the answer to part A. That's the function that it's asking for, right? So let me just box that in real quick because that is the answer to part A, right? Now, part B, right? It says use the function to find the temperature at 12,000 feet. This is really simple. You are literally just going to plug 12 into n. Because again, the function is in terms of n,000 feet, so you're not going to plug in 12,000 feet. You're going to plug in n, right? So you're literally just going to do t of 12, which is equal to 76 minus 5.5 times 12. And there you go. And this will give you, if you were to calculate that, 5.5 times 12, that's 66. So 76 minus 66, that's 10. So there you go. There's your answer. It's 10 degrees Fahrenheit. So basically, all this problem is asking for is asking you to write the sequence, right? Treat it like a function, turn it into a function, and then just plug in a number into the function that you derived. So that's basically, from what I've seen by looking at the lesson, that's as complicated as this is going to get. It doesn't get much more complicated for this, at least for linear arithmetic sequences. Because now we are going to delve into exponential functions and geometric sequences. Okay, so for geometric sequences and exponential functions, they're again in the same way that linear functions and arithmetic sequences are kind of like the same thing. Exponential functions and geometric sequences are kind of like the same thing. So let's look at this. Let's look at this sequence that we have here: 1, 2, 4, 8, and so on. Right. So for here, right, we're gonna look at our formula. An is equal to a naught times b to the nth power. Right. So our an, that's just going to be the term we're looking for. A naught is going to be 1. Right, 1. Now, b, instead of what we're adding each time, it's going to be what we're multiplying each time now. Because instead of adding, like in the last example, we were adding 2. In this one, we're multiplying 2. Times 2, times 2, times 2. So our b in this case is going to be what we're multiplying each time, right? So 2 is going to be our b, and then n, that's just our n, right? So in this case, we have an, obviously the 1, that's, we don't have to write that, right? So in this case, our sequence would be an is equal to 2n. Now, I just want to do a really quick recap of an exponential function, right? because it's very important to understand how these two are linked, right? So now this would be similar to an exponential function. In this case, in this case, f of x is equal to 2 to the x, or f of n is equal to 2 to the n. It doesn't really matter, right? And I just want to show how this function would look like. It's very important to note that this function would look a little something like this. I just want to throw that out there because in the future examples, that shape is going to come up a lot. So I just want you to know that that shape, whenever you see that kind of shape, that's an exponential function, okay? And a geometric sequence, which I showed you how to do really quickly here, is basically going to be an exponential function. Okay, so now we're going to look at a graph here. And if you notice right away, you see this curve that's increasing up as it goes, right? So immediately, that's going to let us know that this is an exponential function or a geometric sequence, right? So if we just write down our values on the y-axis, which I did here, it's 1/3, 1, 3, right? Immediately, obviously, the first thing you notice, we're multiplying by 3 each time, right? So that's going to go on and on. Each time you multiply by 3. So an is going to be equal to your a initial. Now, just like in the first example that I showed you, when we did it with linear functions and arithmetic sequences, notice how it doesn't give us a0 or when n is equal to 0, right? It gives us when n is equal to 1. So we're going to do the same exact trick we did last time. The same exact thing. We are going to replace this. We're going to replace our 0 here with a 1. We're going to replace it with a 1, right? And then we're going to come up here to the exponent, and we're going to subtract 1. So it's the same thing that we did last time. And again, if instead you started with a3, right, you would have written a3 times b to the n minus 3, right? But in this case, we're given 1, right? So we're given our a1. So this is what we're going to do. So we know our a1, right, is eighth or is 1/3, right? So 1/3 times our b is what we're multiplying each time, right? We know we're multiplying by 3 each time. So times 3. And then we're going to raise it to the power of n minus 1. So there you go. There's how you would write that sequence really quickly. And actually, in this case, I'm going to show you something. In this case, this 1/3 is actually equal to 3 to the negative 1, right? So we can actually rewrite this as 3 to the negative 1 times 3 to the n minus 1. And this is just rule of exponents. Whenever you're multiplying two numbers with the same base, you add them. So you get a of n, you get 3 to the n minus 2. So this is kind of just like the condensed version, I guess you would write it, right? So, but this only works when it's the same base. For example, because if this was like 1/2, you wouldn't have been able to do what I just did. But because it's the same base here on both of them, you can actually do that. But again, in most cases, that's probably not going to work. You need the same base, right? So notice what we have here. We have an is equal to 3 to the n minus 2. And if I were to just come up here real quick, we could write that as a function. F of n is equal to 3 to the n minus 2. Now you can, just like we did before, You can use this to calculate other values of the function that you don't know yet. In fact, writing this as a function smooths this curve out, because now you can do your in-between points, right? Because now it's a function. It's not just a sequence. Now you can do like 1.5, you can do 2.5. But that's like getting into like the really nitty-gritty of it, and you're probably not going to do that. For now, this is the answer that you're looking for, writing it as a function. Or again, if it's a different base, you would have stopped here, and instead of a of n, you would have written f of n, right? Now, again, I'm not sure if you're going to be asked this, but let's just say hypothetically, it asks you for f of 0, which again, we don't have here, right? You would literally just plug in 0 here, get 3 to the negative 2 is equal to f of 0, right? Here, let me make myself some space so I can... This is important. Before I erase this, you should know this, that 1/3 is equal to 3 to the negative 1. But so basically, let's say it asks me for f of 0, right? F of 0 is going to be 3 to the 0 minus 2, right? That's going to be equal to 3 to the negative 2. And that is just 1/9. Because this becomes 1 over 3 squared. And then 3 squared is just 9. So you get 1 over 9. So I'm not sure if you're actually going to get asked to do something like that, but I know for sure you will have to do these first couple steps where you get to either this point, or if it's the same base, you can condense it to this point if you like. But I'm pretty sure you don't have to do that. Okay, so this will probably be the last problem. This will probably be the last problem that I do, but a rubber ball is dropped from a height of 25 feet. The ball bounces to 80% of its previous height with each bounce. So before I even go to each part, it's already giving me a rubber ball is dropped from a... This is a typo. You know, that's supposed to this from a height of 25 feet, right? Notice how it's already giving us a height in initial height. Because if you look, it says the ball bounces to 80% of its previous height with each bounce. So basically, the ball's going like this. If this is a ball, the ball's going to go boom, hit the ground, 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 boom. Right? Now, if you notice, I'm going to make this really obvious really quick. If you were to follow the path of the ball, right, you have its initial height, and with each bounce... let me align that more with each thing, right? But if you notice, with each bounce, it kind of makes that curve, right? So if you were to graph that with each bounce as a function, right, it would look like this. It would look something like this. You have your number of bounces, you'd have your height or the amount of feet, and it would look like this, right? Which means whenever we see that curved shape of the graph, we know it's going to be an exponential function or a geometric sequence, right? So we know if we're let's look at our initial, let's look at our function here. We know an is going to be a naught b times b to the n, right? Our a naught, we already know the first height is 25 feet because that's where you're dropping it from, right? So an is going to be 25 times, what are we multiplying by each time? It says the ball bounces to 80% of its previous height with each bounce, right? So with each bounce, as it's decreasing, it's going to be 25 times 0.8, this height times 0.8, this height times 0.8. So because we're multiplying by 0.8 each and every bounce, we know that b is going to be equal to 0.8 and then to the n. So there you go. So the answer to part A, because if you notice, part A says write an exponential function to describe the situation. Well, we already did that. It's right there. So f of n is going to be 25 times 0.8 to the n. So there you go. There's going to be your answer to part A. All right. Now, if we were to zoom in a little more, or if we were to scroll down, right, we have part B. What is the height of the ball at 10 bounces? Now, here you would literally just plug in, since we have a function of the height, we have height as a function of the number of bounces, right? We're literally just going to do f of 10, which is going to be equal to 25 times 0.8 to the 10th power. And that'll give you, if you were to calculate that. Now, what we're doing there is that we're literally just plugging in 10 into our function. That's all we're doing. And this will give you I'll truncate here, 2.684, and then our units is feet. So there you go. So there's the height. So there'd be the height. That's the height after 10 bounces. Right? Now, part C. When will the ball bounce less than 1 foot high? So this is an interesting one, because if you notice, it said when will the ball bounce less than 1 foot high. That's showing us an inequality right there, because it's saying basically after how many bounces will it go less than 1 foot high, right? So we're going to get our function here. We're going to say f of n is less than 1, because f of n is going to be the height, right? And we want that to be less than 1. F of n is obviously just our function. So 25 times 0.8 to the n is less than 1, right? So we're going to scroll down. Now, what we do here is we have to solve for n, right? So 25 times, hold on. So 0.8 to the n, right? We're going to divide 25 on both sides here. So you're going to divide it by 1 over 25. So we know 0.8 to the n is going to be less than 1 over 25. Now, I'm going to show you an exact way to calculate this. It's, I'm not sure if you've already learned how to do this, but what I'm going to show you is by using natural logs. Okay. Now, whenever you're using natural logs, let me write this out. You're going to natural log 0.8 n is going to be less than the natural log of 1 over 25. Right? Now, this is just a rule of natural logs, that whenever you have something raised to the power comes to the front. Okay? So what we're going to have is n times natural log of 0.8, which is going to be less than natural log of 1 over 25. Okay? So now, natural log of 0.8 is less than 1, which means when you divide the natural log of something and that something is less than 1, the natural log is going to come out negative, which means that when you divide by natural log, by the natural log of 0.8, which is less than 1, you're going to need to flip the sign of the inequality. And again, the reason is because natural log of 0.8 is negative. So basically, whenever you have natural log of something less than 1, that's something that natural log is going to come out negative. And whenever you divide by a negative in an inequality, you end up flipping it, right? So now, if you were to solve for this, okay. So once you calculate that, you're going to get n has to be greater than 14.425 bounces, right? But obviously you can't have like half a bounce. So instead of writing this, we're going to write n has to be greater than 14 bounces. Now, this is how you would calculate that, like the mathematical way. But this might be very complicated. And if you don't understand how to do this, there is a much, much easier way. So you're going to go to your calculator. You are going to you're going to go to graph it, right? And you're going to plug in this function right here. You're going to put 25 times 0.8 and then raise that to the x power. You're going to graph it, right? And then you are going to trace, follow along the function, and you are literally just going to look for when it is less than 1. Which, if you do it, wow, would you look at that? It's less than 1 after x is equal to 14. So there's two ways of doing this. There's this way, which is this is pure calculation, and if you don't get the natural logs, that is fine. What you can do is you can graph it on your calculator and then look on the graph to see when y becomes less than 1, which it gives you the same exact answer and has to be greater than 14. Because if we were to graph it, here, I'll just do like a quick little sketch of the graph over here. So you can see if this is 1, right, and this is 14, basically the graph's going to look something like this. It's going to go, and it's not going to go below 1 until just past 14. But that will be it for this lesson. Thank you very much for watching. I hope this helped you understand Pre-Cal lesson 2.2. I tried explaining it as clearly as possible. So thank you for watching.